So for this next question, looking at satellites, this is a common question as well, looking at geostationary satellites, which are really important because if you put the satellite in just the right position, just the right orbit radius from the Earth, then the time period of that orbit is equal to 24 hours. So it takes the same amount of time for the satellite to orbit the Earth as it takes for the Earth to rotate once on its axis, which means the satellite is always in the same position relative to the surface of the Earth, which means you can have satellite dishes on the Earth pointing at the satellite that are fixed. For example, sky dishes do this, so they're all pointing at the same spot in the sky, and as the Earth rotates, it means that the dish stays pointing at the satellite, which is rotating with the same time period. So the first question here is name the force that is keeping the satellite in the circular orbit and state the direction in which this force is acting. So the force is the force due to gravity towards the centre of mass of the Earth, or technically it's the system, but the mass of the Earth is so much greater than the mass of the satellite that the centre of mass of the system is the centre of mass of the Earth. So again, to answer A, the force is the force due to gravity, and it's towards the centre of mass of the Earth. Okay, then on for B, we're just going to use Newton's equation for gravity. G m1 m2 over r squared. Remember, you might see this sometimes with one of these m's replaced with a big M for being the large mass in the system. Cool. And then we just substitute in our values here. Luckily, we don't have to write the units because I'd be here all day writing the units for the universal gravitational constant. And then we divide all of that by the radius. This time we don't have to work out the radius from the surface of the Earth and add to it. The radius of the Earth. Something I will often forget is this little squared down here. I forget to square this bottom term. So then we plug all the numbers into here and we get 67.1 newtons, which isn't a huge force, but that's all the force that is required here. So show the speed of the satellite is 3.07 times 10 to the 3 meters per second. So all satellites at this orbit will be traveling at the same speed regardless of their mass. So here we're going to have to get rid of this mass term, and the way we do this is in the usual way that we've done quite a few times here. We are equating these two equations together. So the force of gravity is equal to mv squared over r here, and then we just need to solve for v, and we've got the value here of fg. So we can rearrange this and we get, I'll show you all the working. First I'll bring the r to the other side, so it's in the bottom over here, so I'll bring it to the top on this side, and I'm equal to mv squared, and now I'll take the m to the other side. It's multiplying on this side, so it becomes divide by on the other side. FGR over m equals, it's v squared, so I'm going to take the squared over as well and just square root all of this side of the equation. Great, now I can substitute in my numbers and solve. So I'm also going to just flip all this around just because of convention. So here we've got the force, 67.1 newtons times the radius of the orbit over the mass of the satellite. So I said earlier that the mass is irrelevant. It cancels out with the mass from up here, but we haven't shown all that working. It will cancel out, and we get the velocity of 3,070 meters per second, which is what the answers, or what the question said it would be. So well done me. Moving on to D. So for D, Kepler's law states that the orbiting object, the time period squared is proportional to the radius cubed. So we need to do two things here. We need to use Kepler's law to estimate the mass of the moon, and in the answer I need to do these two things. I need to derive Kepler's law and use Kepler's law to determine the mass of the moon. So here's my moon with the satellite, again, I've done that tricky thing where you've got the radius of the moon and then the radius of the orbit. Sorry, not the radius of the orbit, the height of the orbit. So you need to add these two together to get the total radius. Okay, so let's start with deriving the Kepler's law thing and showing that time period squared is proportional to the radius cubed. And again, we're going to start in the same place. The centripetal force is equal to the force due to gravity. And we're going to equate these two things again, mv squared over r. I'm going to replace this with big R to mean the total of these two values. G, m, and I'm going to use big M in this case for the mass of the moon, which is what we're going to try and find out. And this is r squared on this side. I'm going to just straight off the bat do some simplifying. The masses cancel out, and one of these radiuses cancels the squared there. Cool. And then I'm going to just simplify this down. V squared equals g m over big R. And now we can use our knowledge of the velocity equation. Velocity is distance divided by time. So in this case, the satellite's going around in a circular orbit, and the time it takes to do one orbit is called the time period. And the distance it travels is the circumference of that orbit. So we can replace d here in the velocity equation with the equation for the circumference of a circle, 2 pi r, and divide it by, this time, the time period. Okay, and this is what the velocity is equal to. So now I can take this and I can take it over here and sub it in place of velocity and then square it all. So 2 pi r over time period squared equals g m over r. And I should have made this big R because it is the total of these two R values. Okay, so then I can deal with a squared here. And now I can, well, I always forget to square this t. Then I can rearrange this and make time period squared the subject, and I get, so I'm basically going to swap these two terms around and bring this r up to this side. So I get 4 pi squared, and this r comes up, so we get r cubed over, and I bring these two down to the bottom over here, g m, and I bring this t squared up to the top on this side. And this is the first part of my answer. So here we've got t squared, and over here we've got r cubed. So this is t squared is proportional to r cubed, which is the first part of the question. And now, this is Kepler's law, now I can use this to determine the mass of the moon. So I'm going to do some more rearranging. I might just come back to this one here and make mass the subject. So I've got mass equals 4 pi squared r cubed over gt squared. And now it's just a simple matter of substituting each of my numbers in. Remember, the radius is the sum of these two values up here. So make sure I add those up. And then cube them. And then divide by these two values down here. So that's the gravitational constant. And the time period here squared. Stick it all into my calculator, and we come out with a mass of the moon like this. Alright, that was quite a lot of work for that last question. Now we're on to the next problem.